Hello, everyone, and welcome back to Simcyp Technical webinar. My name is Xian Pan. I'm part of the Translational DMPK group at Simcyp. I will host the session today. So today's topic focuses on the concentration-dependent blood and plasma binding in the Simcyp simulator. Would you mind moving back to the first slide? Yeah, thank you. So before we start the talk, I'd like to kindly request that everyone stays muted during the presentation. Should you have any questions, feel free to raise your hand or post your queries in the chat box. We have dedicated the Q&A segment at the end, where we will address all of them. We are recording the presentation today, which will be available on YouTube shortly. And the next slide, please. It's my pleasure to introduce today's speaker, Dr. Ian Sorrell. Ian is an Associate Principal Scientist in Mechanistic Modeling Group of Simcyp. He has an academic background in mathematics and physics. Ian has been working in the PBPK modeling field for over 12 years, and he has been with Simcyp for 5 years. I'm glad to have him with us today, and the talk today will cover the concentration-dependent red blood cell binding, plasma protein binding, and also this dynamic binding in the interstitial space. Without further ado, I will hand it over to Ian. Over to you, Ian.
Great, thank you. So I'll start with a bit of motivation for why you might be interested in looking at concentration-dependent binding in blood and plasma. So this is looking at an example of tacrolimus. So this is concentration-dependent blood-to-plasma ratio. So you can see on the left-hand side, there's a plot there of so the dots are the measured blood-plasma ratios against plasma concentration. And you see as the plasma concentration increases, you get this marked decrease in the blood-plasma ratio. So on the right-hand side is what happens when you put this into simulation. So that's the dashed line. So using the concentration-dependent BP. And that's compared to using just a constant BP, and there's a 130% difference in the AUC between the two. So you can see it can make a big difference. And so concentration-dependent blood plasma ratio and FU has been available with a minimal PBK model in Simcyp since version 13, but in version 24 it's been extended, so it's now compatible with the full PBK model. So as with tacrolimus, you can see on the right-hand side, there's kind of 8 other compounds listed there that also show concentration-dependent blood binding, and on the left-hand side, there's listed there compounds that show concentration-dependent binding to proteins in the plasma. So there's quite a few compounds that this applies to. So actually, now I'm going to switch to the simulator. So I'll talk about the different options for the concentration-dependent binding. And I'm going to talk about the options on the PhysChem and blood binding screen for doing this concentration-dependent binding. I will briefly mention that some of this can also be done in TMDD and the reasons why you might want to choose a different model from these different options. So for the blood plasma ratio, to use concentration dependence, there are 2 options. So you have the concentration-dependent profile, BP profile, and then you clicking on that button opens up the pop-up. So then you can enter in your the profiles, the concentration, and the measured blood plasma ratio values. And so each individual in your simulation will have a slightly different profile, and that's because they'll each have their own hematocrit kind of value, and that will be then adjust the profile relative to the reference value that you can adjust if you want to, if you have information on that. So note also that the lowest value of the profile, the BP ratio, that 0.8 there, that's used in the baseline over on the right-hand side. And that value does impact some of the calculations in the simulator. So it might be if you're simulating your concentration is kind of much lower than the kind of highest concentration you've got, you might want to look at the sensitivity of your results to that kind of baseline value, although typically doesn't make a big difference to the simulations. So the other option for including the concentration-dependent BP is the semi-mechanistic binding option. So I'll talk a bit more about that when we get to the slides. but there are two parameters for setting that. So the maximum erythrocyte to plasma value ratio, and then there's a constant term. It's just describing the complex, so the KD value for the complex. Okay, so that's the BP terms. Then for the fraction bound in plasma, so again there are two options, quite similar. So you have a concentration dependent FU profile. So it's kind of similar again. This time also the individuals will have slightly different profiles, and that's based on the reference value of the selected binding component compared to the individual's kind of value they have for their plasma concentration of that binding component. And then the other option for specifying the concentration FU is if we click on the specify KDs, and then also the concentration dependent FU from KDs. So in this case then, we have the concentration dependent FU is determined by the concentration and the KD value for the selected binding components. And so now you can choose up to 3 different binding components. And what you can have is that so you can have 3 different ones, but the user-defined other component. But you can also select that other component to be identical to AGP or the albumin. And in that case, it's you're simulating having 2 binding sites on one of these proteins. And to do that is in the population blood screen. So here's all the information in terms of setting the distribution, hematocrit, and the AGP and the albumin. And it's also where you can select or enter the information for the user-defined plasma binding component, and you can, if you want to do say 2 binding sites to AGP or albumin, you can select that there. Okay, so that's the different options for doing on the PhysChem screen for choosing these concentration dependent terms. So on the distribution screen then, once you've selected those, there are some other options that become available. So with the minimal PPK model, you have the option of turning on the concentration dependent volume or not, and that's just then so the volume of the systemic compartment changes depending on with the fraction and bound, how that changes. So that will just the tissue partition coefficients which are used to calculate the kind of volume of the systemic compartment. So if you select full PPK, so this is automatically turned on so that the tissue partition coefficients they will account for this concentration dependence. That's using because they depend on the fraction and bound in the plasma. So when you have the full PPK on, that's they're always they will depend on your concentration dependent FU. A new option in V24 is doing the concentration dependent interstitial binding. So in this case, so as well as looking at the binding to the proteins within the plasma, in the blood, it also looks at accounts for the concentration dependence of the interstitial binding in the interstitial space. Sorry. So I'll talk about that more later in the presentation. Okay, so that's I think. Oh, so one thing, with the concentration dependent binding, you need to know the tissue to plasma protein ratios, and they're entered on the tissue composition screen. And so normally the KP other one is all zeros by default. So if you want to use your own user defined kind of protein, then you need to determine the tissue partition ratios for each tissue. Okay. So now I'll go back to the slides. So hopefully now these slides, the first few slides will just be, we'll go through, it should be just a recap of what I've just said, and if there's anything I forgot to say, well, I'll include that. So as mentioned, with the concentration dependent BP profile, the hematocrit reference value is used to adjust the individual's BP profile, and the baseline that's used to calculate some of the properties, the compound properties that are used in the calculating the partition coefficients. Then for the semi-mechanistic model, so now I'll introduce, this is the formula for the semi-mechanistic model. So you can see the input values, the Bmax and the Kd, how they interact with the plasma concentration, and also in the formula we have the individual's hematocrit and fraction bound in plasma. In this case, the baseline value is also using the same kind of calculations as previously, but now it's set using this formula, but with the CP set equal to 0. So also introduced the FU profile. Talked about how the individual FU accounts for the protein concentration of the individual for that selected binding component. And in this case, the baseline FU, again, that's used for some calculations simulator. That's a low concentration is used to determine the baseline FU. And from the concentration dependent FU from KDs, so we talked about how we can have multiple kind of binding components, and that can be 2 binding sites on either albumin or AGP. Okay. Then also on the blood screen, so we talked about how we can use the set the user-defined protein to be identical to AGP and HSA. And one thing to note about the albumin is that you can see there's a high concentration of albumin compared with AGP. So that concentration for a pop rep individual is about 703 micromolar. So that means so if you want so if you're seeing concentration dependence and it looks like it's due to plasma protein binding at much lower concentrations than this, it's probably not due to binding to albumin. It's probably there's maybe binding to another component within the plasma. So also mentioned about this concentration dependent volume, and that's an option for the minimal PPK model. And that's then, but with the full PPK model, the concentration dependence volume is always on, and that's because the FU is used in the calculation of the tissue partition coefficients. So I mentioned at the start that from version 24, the concentration dependent binding can be used with full PPK, so it's been available with minimal PPK for a long time. It's not, you can't use many of the permeability limited tissues with the concentration dependent binding, although you can use some of the kind of quite important ones in terms of the liver and at least the standard permeability limited liver model and METKIM, the kidney model. So, so other tissues, you can't use those when the concentration dependent binding is active, and that includes the multi-compartments of the zonal liver. So I want to mention a bit of a comparison with the concentration dependent binding that you can do with the target binding, so the TMDD. So there's a webinar on this a couple of months ago that's available on YouTube if you want to have more information on that. So with that you can look at binding to a protein in the plasma. And one thing, the extra thing you can do with this is you can look at kind of slow binding kinetics or just different binding kinetics, because you're specifying, as well as the so just a KD, you have the K on and K off. So with that you can also look at irreversible binding. So in V24, the interstitial binding, you can't do that. You can just look at the kind of binding in the plasma. But it's interstitial binding is being added as an option in V25. And there's only a single binding site. So in terms of concentration dependent binding that we've been talking about today, that's just for reversible binding, and the assumption is that you're rapidly reaching an equilibrium between the bound and unbound. One advantage is you don't need any knowledge of the kind of protein that's binding to if you have a profile, and you can also do multiple binding sites. So a new option that's added for V24 that could well be useful when you have concentration dependent FU is instead of specifying the total renal clearance, you can now adjust it to use the unbound renal clearance. So then your renal clearance depends on the fraction unbound. So there's an example here of ertapenem. So for low concentration, you'd have kind of these two simulations, one with using the total renal clearance option and the unbound renal clearance option. You would have pretty similar kind of amounts of the which is the urinary recovery, but a higher concentration, because the ertapenem has a concentration-dependent FU, the fraction bound is increasing as the concentration is increasing, and so using the unbound renal clearance option, we see this you're getting this higher amount of urinary recovery of the compound. So the outputs you get probably what you'd expect, maybe. So you can output the BP profiles of all the individuals and also the FU profiles. You can also output all the tissue partition coefficients. As I said about these change, or they also become concentration dependent. So you can output all those for all tissues for all individuals. And a new output that's been made available in V24 is the time-dependent volume of distribution. So this is just calculating, taking the total amount in the tissues and dividing that by the plasma concentration at each time point, and also the body weight, so it gets into liters per kilogram. And so the figures there are just results of a simulation, or two simulations. So one using constant FU, that value there indicated by the horizontal yellow line, and then turning on concentration dependent FU for another simulation that goes in the green line. So you see how that's changing the FU over time, and you see then the impact. These are the two same kind of simulations looking at the impact of the volume of distribution, and you see there's quite a difference between the two. So now I'm going to talk about concentration dependent interstitial protein binding. This is also new for V24. So the idea is that obviously there are the plasma proteins, as well as being present in the plasma and in the vascular space, present in the interstitial space. There may be in some tissues, particularly the brain, they're at a much lower concentration in the interstitial space. And the calculation of tissue partition coefficients I've always taken account of these proteins, the protein binding in the interstitial space, but normally that's assumed to be independent of concentration. So the new option that I showed again there on the distribution screen, so selecting that concentration dependent interstitial binding, when you have, it's only available for methods 2 and 3, that then you also take account of the concentration dependence in the interstitial space as well. To be able to do this, you need to know, so it uses the same KD that's used on the PhysChem screen for the plasma binding, but you need to know the protein plasma concentration, and for all the tissues that you need to know that the protein tissue to plasma ratio. So I said this option is available just with method 2 and 3, and it's available when the concentration dependent FU from KDs is selected. But it's only uses the for the actual interstitial concentration dependence, only accounts for the albumin and the other protein. So it doesn't account for concentration dependence in the interstitial space to AGP. So AGP will contribute to the systemic FU in terms of the concentration dependence if you have this selected when running the simulation, but then a warning will be shown to say that it's not being accounted for in the interstitial binding, and that's just because we didn't have kind of enough literature values for AGP to give for the tissue to plasma protein ratios. But there is a way of estimating that if you do want to include AGP, and it can also apply to any other kind of protein. We have kind of some basic information to estimate what those tissue to plasma protein ratios are. So yeah, as I said, so the AGP is not included in V24 because we didn't have, there wasn't limited literature data on that and those ratios. So, but there is, we do have, so we already has these tissue to plasma ratios for albumin because they were already used in the simulator. And so by default, as I said, the other one is always set to 0. So these need to these parameters need to be populated if you want to kind of include a novel protein for interstitial binding. To note that the liver ratio, as well as being used for the interstitial binding, is also used in the liver permeability limited model. So if you want to include, say, a novel protein, a different protein, a used protein, and you want to use the liver permeability limited model, you should really estimate the liver tissue to plasma protein ratio as well. And also when you choose the interstitial binding option, that overrides the protein binding defaults for the compound type. So I mentioned that so the tissue partition coefficients calculation of them always takes account of binding to proteins, depending on the compound type. But you don't sort of have any control of that normally. So normally, so if it's a neutral compound, it's assumed the binding is to lipoprotein. So it uses this lipoprotein ratio. That's what this column is there for in the middle. For an acid or weak base, the binding is assumed to be to albumin. And for a strong base, so no protein binding is included there, but there is binding to acidic phospholipids. So when you turn on the concentration-dependent interstitial binding, then whatever component you have selected, so if it's albumin or the other component, then that is used to determine the binding. So the neutral, so if you have a neutral compound and you have albumin selected as your binding component, then that's what's used to calculate the tissue partition coefficient. Okay, so just an illustration of what that impact can have of turning on the interstitial bindings. There's just two simulations running, and just the only difference is just turning on that interstitial binding option. So that's when the option is on. So that's the green line, and the red one is where there isn't the interstitial binding. So one thing to note is, so you can see that in the top and middle there is a difference in the systemic plasma concentration. But one thing that's probably driving this is the difference in the kind of particularly, so I've got here the liver partition coefficient. You can see that when you have the non-linear concentration dependent interstitial binding turned on, there's not much the change. There's less change in the kind of liver partition coefficient. So the interstitial binding option is I think more mechanistic, includes more accurate, but it does require more information to be able to use it. So a lot of these tissue partition coefficients. So you can estimate that. We have a way of estimating that using the Simcyp biologics model. So the data you need for that is the molecular weight of the protein. So we've got an example of the AGP and the plasma concentration. So also, if you have a synthesis rate, you can include that as well in a tissue or multiple tissues. So the method uses kind of the new soluble target feature in V24, where the steady-state interstitial tissue concentration of the soluble target for each tissue are derived for initial conditions, and they're reported on the TMDD sheets. So essentially, you can run a simulation where you've set using your information to define a soluble target, and then using that to calculate what the tissue to plasma protein ratio is, and then you can input that in the tissue composition screen. So we've done that for AGP. So here's just the examples here for what we get when we account for synthesis in the liver and no tissue synthesis. You see the only difference is kind of the liver ratio there. Okay, so just to summarize, so the concentration-dependent binding is now available in V24 with a full PBPK, whereas previously it was just with a minimal PBPK. And your choice of the kind of phys chem and blood binding concentration-dependent options versus the TMDD depends on the application, the kind of information you have available, particularly on the kind of target of the protein it's binding to, and the dynamics that you're interested in. Some functionality, so particularly that some permeability limited tissues aren't, you can't use them at the same time as when you're using concentration-dependent binding. The interstitial binding is more mechanistic, but also may impact simulation speed. So one thing I didn't mention was the simulation will show that if you're getting some of these options can cause the simulator to slow down. So you might want to change the solver from either Livermore or the CVODS default stiff. And which is that with that interstitial binding, to get the tissue to plasma protein concentration ratios, we do have a way of estimating that. So if you're interested in that, you can contact us to find out how to do that. And also on that, there's also publications in preparation on prednisolone that uses this concentration-dependent interstitial binding, and this kind of method for estimating proteins. So prednisolone binds to transcortin. So the transcortin tissue to plasma protein ratios kind of were needed for that publication. So they've been estimated. So hopefully that's published soon, and you can look at that as well as an example of how to use this concentration-dependent binding. Okay, thank you. So I'll stop there and see if there's any questions.
Thank you, Ian. And now let's move to the Q&A session. So if you can either raise your hand or type the question in the chat box. So the first question is from Florent. He's asking if you have any recommendation as regards to the procedures and experimental conditions set for the in vitro study of protein and blood binding.
No, so I don't particularly have any recommendations for that. In terms of the in vitro studies. So it depends if you're, so it's perhaps, I mean, obviously, you need several concentrations, quite a lot of concentrations possibly for looking at this and understanding where you're getting the dependency and kind of but I guess understanding the concentrations you're interested in before you do the in vitro tests, I guess is a good idea. So you at least get some idea of where to what concentrations to use. That's probably not particularly helpful, but that's I don't have a lot more on that one.
Yeah, I agree. I think the concentration, how to find the most relevant concentration relevant to your in vivo and then have that covered in your in vitro study is important. You don't want to run the in vitro study, then find out that's from the in vivo that actually fall off your measured range, and then you have to do some extrapolation. Or if you want to, the purpose to see the saturation, you might want to say that from in vitro. But again, you need to, as Ian mentioned, to find the most relevant ones. So while waiting for, okay, there another one. So David, you can unmute yourself.
So when you set the other tissue equal to be equivalent to albumin, does it dynamically change that concentration with the demographics like it would albumins because it's age and sex related?
Yes, so it's the other protein. Is it for each individual? It's like a copy.
Okay.
So it's always the same value for each individual. So if it's, I presume it's the same for. I've not looked at the.
And then a similar question is when you do that set it to albumin, do the tissue albumin to plasma ratios for calculating volume get set to what albumin was for the other tissue, or do you have to do that manually?
So that you have to do manually.
Okay.
So, yeah.
And one other nice addition for future versions would be for biliary clearance, the simple biliary clearance, to also have it similar to unbound renal clearance and have that option there.
Okay. Yeah. Sure. Yeah. So,
thank you.
Yeah. Okay. Thanks.
Okay, just if you got any questions, please either raise your hand or type in the chat box. So while we're waiting for other questions to come through, maybe I can ask a question. So there are multiple options when we're doing the concentration-dependent red blood cell binding or the plasma binding. So we could either use user input profile, concentration time profile, or use like relatively mechanistic model, like semi-mechanistic model for BP or the specific KD for FUP. Do you get any suggestions? Which one should we try? Should we try both, or any suggestion how to select the model?
Yeah, I think for the BP, the profile and the bindings should give you similar results if you enter them in. I guess one advantage of the semi-mechanistic is then if you want to look at, say, sensitivity, it's easier to do that with the Bmax and the KD rather than having the kind of profile. And also, kind of if you've got a lot of points on the profile, kind of fitting that semi-mechanistic model is something you probably want to do. You do outside of Simcyp. So like that tacrolimus example, some of the noise maybe in the data you'll kind of because you're fitting a model to it, you're kind of using data from all the points at each concentration to kind of so it might not be quite as noisy a profile. It might be the simulator might behave better as well, actually kind of using the semi-mechanistic binding option. For the FU, I'd say the specifying the KDs just has the benefit of being able to use the interstitial binding option. So you can't do that with the FU profile.
Yeah, all right. Thank you, Ian. I think we're close to the end of this webinar. Thank you, Ian, for the talk about the concentration dependent binding in the simulator. And thank you to everyone for joining us, for your attention and active engagement. Should you have any additional queries later on, please don't hesitate to get in touch with us. And our next technical webinar is scheduled on the 10th of July, which is about the biologics PBPK platform in the Simcyp Designer. So if you're interested in it, please register through members area. Once again, thank you for being with us today, and we look forward to seeing you soon. Wish you all a lovely day and goodbye.